Okay, so I'm actually flattered that so many people decided to come. I hope you didn't come here because it's the only place with air conditioning that you can quietly and in peace tweet messages. Jim Weber had a funny talk in the morning about graphs, and this is some sort of continuation of that. It's still about graphs, about a special kind of graphs, about state machines. The FSA, the finite state automata, that has become a buzzword for some reason in Lucene and Solr because Mike wrote code that accelerated certain routines 100 times. So people all of a sudden got the idea that they can accelerate anything 100 times. That's not going to work this way. But it is a good opportunity to actually bring this data structure back from the, wherever it was lost for the last 40 years, because it's actually cannot be considered a new thing. And that's why I'm here for. So I really admired Jim's presentation. It was funny. How can you make a presentation called like this funny? You can't. So I was thinking maybe, I'm not going to put so many pictures on it, but maybe go back to the roots. Do you remember the time when you first saw a slide transition? Like something actually sweeping in, like, it was like, boo, wow, so cool. So I decided to do something like that and go back to the roots and actually prepare some hardware accelerated transitions for you this year. So, oh no, sorry, that's not, see, that's the wrong thing. There you go. Boom. Aha! Yeah, see? Thank you. And that's about it. Thank you very much. No, so there'll be more, but in between, try to focus. So my name is David Weiss, or Dawid Weiss, depending how you pronounce it. I'm from Poland, and I really like coding. I was coding for 10 years in assembly only. So I like low-level structures. Like, you can't really scare me away with pointer. I mean, a pointer, I don't understand. An address in memory, I do understand. So it's really something I was doing for a long time. Then I went to academia. I did my PhD in information retrieval. I am present in the open source arena. I write Caret Square. It's our software for grouping, clustering, semantically text documents. If you want to check that out, go to caret2.org. And as of now, I'm on leave from the university where I've been teaching for the past 5 years, and I'm focusing on my own business. So if you're interested in text clustering, please get in touch with me or Staszek right here. He'll be giving a talk later on. But today, I am going to talk about state machines in finite state automata. And what I wanted to do is give you an intuition of what it actually is, and that's simple because it's a simple data structure. I wanted to give you an intuition how algorithms are running on this data structure and why they're so fast, most of the time. But I also wanted to show you how these data structures are used in Lucene and Solr and where they're good at and where maybe they're not good at. I will not give you code snippets because the API is shaping fast. I mean, the changes are done right now, and the code is changing. Whatever we need it, we change it. It's in trunk right now. It's been backported to 3.02. That's just been released. But really, don't get too attached to it because we like to change it to make it easier, hopefully. Aha! Okay, so the first part is demystifying the acronyms a little bit. There's been a lot of acronyms running around, DFAs, FSAs. What are these? So let's take a look at what finite state machines are, or what state machines are in general. A state machine is a collection of states, and these are the circles here, and transitions, or links, or arcs, And these are the arrows that point in between states. As you can see, the transitions can be labeled, so they can have a symbol on them. It doesn't have to be a letter. It can be something else, but let's just assume there are letters of Latin alphabet for now. So what this particular state machine encodes is a sequence of 4 words, is a set of 4 words. And those of you who are German should recognize it. Right? Ich bin ein Berliner. Right. So, you know, a data structure like this can be used to recognize sequences coming from the input and tell us whether a sequence matches or not, whether it exists in the finite state machine, in the state machine or not. This one is not finite yet. So what the algorithms actually work like is, the best way to imagine it is by coins. Like if you had coins and put these coins in those states, and the only operation you're ever going to do is move those coins around. And you know, instead of imagining, let's just do it. So let's start from the starting state. This is the Polish coin with the what's the word for it? Eagle. With an eagle. You can't see the eagle, but it's there. So we start from the starting state. It's the default state, and now we have 4 options. We can go along these 4 transitions. Each one of them is labeled. Let's say we want to accept or check if it exists in this automaton. The sequence is bin, okay? Bin. So the first symbol from the sequence is B. Can we move this coin on any transition that has B on it? Well, of course we can. We can move it right here, or, and this is the tricky part, because there are 2 transitions labeled with B, we can duplicate the coin. So we can put another one and move it right here, right? Okay. Now we have 2 active states in this state machine. And that's about the only operations that the actual software is ever going to do. It's going to track those coins and push them around between states. So game over. That's it. That's the whole data structure. Now, the tricky part is coming up with the use cases for the data structure, as in most of computer science. Data structures are easy. It's just the application of these data structures that gets tricky. So the next symbol on the tape is I. Take a look. The first coin, we can follow the transition on I. We push it to the next state. This one, it doesn't have any outgoing transition labeled with I. We just remove it. Right? Okay. Next symbol is N. We move the coin. This black state over there is called the acceptor. So it's the final state saying, yes, there was a sequence on input when building this state machine that has been recognized. And if we had more symbols on tape, if there was, I don't know, binary on input, we wouldn't have any outgoing transition. We would take the last coin out and we would be able to tell that no such sequence existed. Because it's the last symbol on tape, we're at the terminal state, an accepting state, and we can say, yes, bin was present when we were building this automaton. All right, example over. Right. So that's a visual indicator that we have accepted the string. Now, that automaton, that state machine that we've just seen, was not deterministic. Deterministic, basically the intuition is there is, at any given moment in time, there is a single coin, ever. So at any given time in this automaton, when accepting input, there will be either 1 coin or 0 coins, meaning the input is not accepted. And that's what finality determinism. That's why you should pay attention when you're talking. That's what determinism is, okay? To make this automaton deterministic, to make it, you know, always have a single coin on it, we would need to rearrange these transitions, these 2 red transitions. And right now, no matter what input you give to it, there will be always a single coin running through it. Right? How this actually, you know, what to do to make it minimized, to make it deterministic and minimal, we'll talk about in a minute. Okay, so the distinction between different types of automata right now. You can have the different variants of these terms come together, non-deterministic, non-minimal, deterministic, non-minimal, blah, 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 blah. These different types just mean what the state machine is built like. So, for instance, the top one here, it's non-deterministic because from this state here, you have two transitions labeled with the same symbol. So you would need to duplicate the coins, right? So it's non-deterministic, and it's also not minimal. Minimality means there's as few states as possible. There's no way to create the same state machine that would accept the same input language with fewer states. Okay? And actually, all these state machines are equivalent. They accept the same sequence. They accept kill and bill, right? But this one is deterministic, but it's not minimal. Why is it not minimal? Because you can create this machine, this state machine, that accepts the same input with fewer states. And the last one is actually both deterministic and minimal. You can't make it, push it into fewer states. Hope it's clear. All right. So going back to data structures that we all know, imagine you want to emulate a set of strings, a set of sequences of characters. And we have three sequences that we would want to put in that set. That is Lucene, Lucid, and Lucifer. I'm sorry for guys working for Lucid, but Lucifer just happens to be the next word in my dictionary. Really, I'm not an evil person, but that just happens to be like this. So Lucifer is, lexicographically, it's the next word after Lucid. It has a nice hash code. You would life. You'd know how to create a hash set out of it. That's clear. Now, how do you emulate a set of these strings based on an automaton? The same way I've just shown you. So you create a minimal or not minimal state machine, and it's shown right below. And you can check for existence of any input set of string characters. And the only output you'd get as, yes, it exists, is for Lucene, Lucid, and Lucifer. That's the only strings that are accepted by this state machine. But there are actually two other things worth of noticing right now. On the state machine, you get two more operations, at least two more operations. One is, for a given prefix, like LUCI, you can actually get the lowest matching sequence and the highest matching sequence in lexicographical order just by following the lowest outgoing transition, the one marked with the lowest lexicographical symbol. So in this case, it would be you follow to the prefix so that you're in this state here, and then the lowest matching would be D. So the lower bound of the prefix Lucy is Lucid, and the higher bound is Lucifer. Okay? And this way you get the lowest one and the highest one matching, and that's actually really useful in Lucene and Solr. So just, a thing of note, it's actually more useful than just a hash set. Now, another thing you can do with state machines is emulate a map, an association between keys and values. And the way it works is, technically speaking, it's called a transducer. So it converts the input sequence into the output sequence or whatever there is. So imagine we have a hash map of, a sorted map, in fact, of keys, same keys, in values, 1, 2, 666, all integers. Without delving into details, the way you would like to encode this information to actually be able to retrieve it back from a state machine is by putting certain things on the transitions. So as you traverse this state machine and you follow a transition, you accumulate. And take a look at this example here. Let's say we are accepting input Lucid and we want to see what's the output for Lucid. You go along the first transition and it has the output 1. So you accumulate to 0, the temporary output is 1. You follow, then the next transition with an output is this one, it's I. So you accumulate 1 to 1, it's 2, and then there are no transitions with output. So once you reach the final state, the output for Lucid is 2. And I'm not going to tell you how to make that work algorithmically to get the state machine like this, but it's actually trivial. So the common part of all the outputs gets pushed toward the root node as far as possible. That's what happens. And again, if you can store keys and values in a structure like this, it turns out to be very, very useful. One more thing that I would like to highlight right now. Note that the shared prefix between all the keys stored in the state machine are actually conflated into a single path. So no matter how many strings you have, if there's a shared prefix or a shared suffix, it'll just be stored as a single path. And this amounts for insane compression ratios if you do have this property of repeated suffixes or repeated prefixes in your input, which most of the languages that are, inflectional do. So that's a great property. All right, just check on time. Oh, just have the German, okay, good. All right, so the construction algorithm. I'm not going to talk about that, that would take too long. If you're curious how it works, just find me somewhere and I'll try to explain it. It's really simple. The interesting thing is, if you have sorted sequences, you can build a minimal deterministic state machine in linear time. You can build it right away, in almost time proportional to the size of the input. So it's blazing fast. Having said that, once you know what FSAs are and FSTs are, let's take a look at how they're used in Lucene and Solr, and maybe that will clarify some use cases, potential use cases for the future as well. So I must say, right now the situation is a bit confusing because there are two packages in Lucene and Solr that implement state machines. Two packages that have absolutely nothing to do with each other than the logic, the intuition that they actually implement state machines. One is util automaton, and this package is a partial port of the Bricks library by Anders Møller, if I recall right. And this package is used for fuzzy queries, for all kinds of automaton queries, and I'll tell you exactly what it works like in a minute. The other package is util FST, and this package is used for improving index performance and for suggestions right now in Solr, so for Autocomplete in Solr. And okay, and just taking a look at the examples and actual implementation of this, and this is the only two slides that actually go beyond the level of regular intuition. These are the hardcore slides, but Mike McCandless insisted that I put it because he loves it. So everything I've said about state machines is correct. The intuition I tried to convey to you is correct. Now, unfortunately, the implementation in Lucene is a little bit different than what I said. There are basically two different ways to represent state machines. One is called Morse representation, and the other is called Mills representation. One is compact and intuitive. Well, one is compact and not intuitive, and the other is more verbose but more intuitive. Now, guess which one was the one I was talking about? That was Morse representation. What it boils down to is, in Morse representation, states are explicit. So I actually walk along states, push those coins along states, along transitions to states. And there are final states where you can say, yes, I've accepted some input. In Mills representation, and this one is shown on the right, this is an equivalent state machine. In Mills representation, there are no states. The finality is represented on the transitions. So as you walk along the transitions, if you follow a transition marked as final, you can say, yes, I've just accepted some input. And you go to some other nodes or states, but there is no physical representation of states. You just follow to the first transition of the next state, or the target state. So because there is no representation of states, just transitions, it's much easier to represent it in memory because there's just a linear, list of transitions. There are no states. Okay, so that's about it you need to know for now. The other thing Mike wanted me to tell is next state chaining. And I'm going to make it brief. So the thing is, when you have those pointers, those transitions that we have nicely shown as arrows on the picture right here, when you have those arrows, they're actually pointers, right? So they need to be pointing to something. Now, in a state machine, to represent it, you try to minimize the numbers of the number of these pointers to make it as compact as possible. And it turns out that in many cases, a state machine is just a sequence of states that have a single outgoing transition. So it's like, circle, transition, circle, transition, circle, transition, circle. And that would mean we have a single transition, single transition, single transition, single pointer, single pointer, single pointer. So instead of adding pointers, we can just say, yes, this is a state with a single transition, and the state that points to it is right next to it, right? We can't do that. I know it's quite complex, but bear with me. So what Mike did, he implemented this fancy way of serializing state machines, which serializes as it creates a state machine. As soon as it's created and we know that the state is never going to change, we can serialize it. We can push it to disk or to RAM, to whatever. But a problem comes when you have a state for which you have two transitions, and this is the S3 state here. So you have two outgoing transitions, A and B, and here are the pointers. A pointing to S2, and B pointing to S4. But in this representation, you wouldn't be able to tell which one is, you can't do this optimization with the next flag. You can't really get rid of this transition here. So what he did was he reverses the order of transitions, and this way he can always say, okay, if the first transition has the bit N set, it's the state that starts right before it. So what I'm going to say is, briefly, is the intuition is pretty clear and easy to follow. Once you dig in the code, that's like, you need patience, piece of paper, and probably sometime around 3 or 4 in the morning, you're going to get it. But it's interesting, and it's fun stuff. And the point of it is to make the automaton as small as possible. And actually, in Lucene right now, these automata are very, very efficient. I just wanted to show you an example. We compressed terms list from Wikipedia, full terms list from Wikipedia. The input is 481 megabytes. It's about 38 million terms. And the automaton for that is 258 megabytes. And that's a data structure you can actually use for lookups right away. So it's something that is right away ready for traversals. If you zip this thing, it's going to be only 100 megabytes smaller, but it's not useful, out of the box. If you have highly inflectional languages like Polish, where suffixes and prefixes are pretty much, repeated all the time, 162 megabytes of input, 3.5 million sequences, terms in Polish language compresses into 3 megabytes. So that's like nothing, These squares here actually represent the area, the relative size of each of these data sets. So it's an efficient data structure, really, really memory efficient and friendly. Okay. So the first use case, the first real use case is autocomplete. And there are no excellent solutions for autocomplete. Every autocomplete is really depending on your use case scenario, what the data is, what the users are, what they're looking for. But typically, a search box, when you type in something, you expect, how come I have 15 minutes? I have more. Okay. Typically, when you type in a prefix, you'll get a list of suggestions sorted by some score. These suggestions are taken from a query log or from the index. So in Solr, you get 3 different implementations of doing that: JASPL, TST lookup, and finite state machine-based lookup. Now, again, to implement it, and people have been complaining that there are no recipes for implementations. This is a recipe for implementation. So if you want to do something, on your own, when you get back home, this is your homework. A simple, naive implementation of a suggester would be like this. The input terms that you want to suggest back to the users, you concatenate them with the scores that they have, for instance, determined from the query log. And here we have 4 terms, 4 scores, right? You know which ones are scores because you put the vertical bar between the term and the score. If you build an automaton out of it, you're done. Because take a look. If you follow the prefix, like FOU, if you follow the prefix in this automaton, you end up at a node from which every single path that is accepted forms a completion. Because these were the input sequences that you got when building the state machine. So the only thing you need to do is collect these, maybe sort them or insert them into a priority queue, order them by score, and you're done. You can return them to the user. The problem is, for short prefixes, you end up collecting a lot of different paths, and that's what you wouldn't want to do. So let's try to improve it. What you can do is move the scores from the end of the terms to the front. Now, when you compress something like this input into an automaton, the root node, every transition leaving from the root node is actually the weight. So starting from the highest weight, you follow, again, the highest weight, follow the prefix, and then you have lexicographically ordered completions for this prefix with the highest weight. Now, if that's not sufficient, you follow the next one in order, the next score in order. Again, follow the prefix FOU, and then complete, collect as many sequences as you need. And note that there is no priority queue, there is no sorting, that just gives you the result right away. So it's constant time collection of suggestions, there is no overhead at all. If you're really inclined on making phrase suggestions or infix suggestions, that's the same algorithm. Instead of putting the whole terms, you put every single infix, you put it into the automaton with the given weight, and postfix it with the phrase or with the term it originated from. Now, what you end up with is, okay, you have the user type in, of course, I don't expect you to understand it, but the mechanism is the same. You follow the highest score, you follow the prefix, and you collect everything that completes this prefix, and then you do have the entire phrase that formed that prefix, that this prefix originated from. The thing is, like I said, suffixes that are the same conflate into a single path, so there is no memory overhead. That actually is pretty darn small data structure. Constant time lookups, regardless of the dictionary size. And the only problem is that this data structure needs to be built in batches. It's not an online system where you can add and remove stuff. It needs to be built in batches. But most people do it anyway. Just to tell you, just to show you how fast it is and how small it is, this is a comparison of 50,000 terms. So that's the size, the circle is the size of the data structure needed to encode it. So it's 300 kilobytes for the FST and about 8 megabytes for the other implementations of the suggestion in Solr. And the same with times per query and queries per second. Queries per second are numbers here. If you shorten the prefix, the existing implementations like the ternary tree and JASPEL, they just slow down. They slow down significantly because they need to push so many completions into a priority queue. With the state machine, the performance pretty much remains the same because there's no sorting. The data is already sorted in the state machine. Okay, so finally, another use case are automaton queries. Imagine you have a regular expression that you want to search documents with. Now, the way it was done in the past, the regular expression would be compared against every single term in your index. And the terms that were matching would be promoted, and then a full query would be made. It can be done a little bit different. If the regular expression, like this one, if the regular expression expands into an automaton without loops, then that is a condition that is unfortunately required. Then we can, from this automaton, we can extract every single term that it accepts. So the whole language state machine accepts is readily available right away. And what we can do is, instead of checking against every single term, we can enumerate all the terms from this state machine and just skip to these terms on the terms position list. And that accelerates things a lot, because if you have a long terms list, you do just a few skips along and you get the result. Both automaton queries, regex queries, and wildcard queries right now use this technique, so that's where the acceleration comes from. It's the way to actually skip certain terms in a fast way. Just be aware that there are two implementations of regular expression query. One is regex P, and that P actually is the automaton query. I'm fine, I'll make it. And there's another one called regex query, which is using that regular expression technique that I mentioned at the beginning. So it actually scans through all the lists, through all the terms. Now, these were regular expressions. Now, you're probably aware of fuzzy query technique. So fuzzy queries meaning, I'm looking for a term that is within a certain distance from my term. I'm looking for all the documents that have terms within a certain distance. Like, I'm looking for cat, but pat will also match because there is a single letter changed in that. That is expressed with Levenshtein distance. There are three operations. Technically, there are three operations: addition of a letter, removal of a letter, and substitution of a letter. And the Levenshtein distance is the minimal number of operations that gets you from one to the other. I'm speeding up. Okay. The point is the Levenshtein distance for a given term. You can build an automaton that encodes the whole universe of all the sequences accepted for a given term with a given distance. That algorithm is understood by about 3 people in the world. One of those people is this guy. The other 2 people are Robert Moore and Michael McCandless. I tried. Mark Miller also understand that? Darn. Mark Miller is like beyond this guy. Yeah, probably the author probably understand that too. It's actually, the intuition is pretty simple, but the actual gory details are not. So I'm going to leave you with that paper for those long summer nights, winter nights. Don't waste your summer nights. But the intuition is like this. An automaton for the term Lucene and distance 0 is actually just a chain of states accepting the term Lucene, right? That's simple. An automaton for distance 1 from Lucene, and that actually makes sense. Wait, don't laugh, that makes sense. Look, the first path going out of this is U, C, and probably the rest of the string. So it's the deletion of the first character. Now, the second path here, this funky looking thing, is substitution of L with any other given character from Unicode. And then you can go U, C, etc., etc. That makes sense, you know, it's really logical. You just do every single possible combinations of these operations, and the whole universe of these terms appears right in front of you. Now, the level 2 automaton for Lucene, and let me just explain it in detail. No, sorry. No, but I couldn't resist. I mean, it's beautiful in a way. Like imagine a wallpaper like that, you know? I don't know, give your girlfriend's name or something and make her a birthday present. Just print. Honey, this is your Levenstein 2 distance from your name. It's like, did you just say something ugly to me? Yeah, that's really something. But the mechanics of this is pretty much the same as with regular expressions. So you have this huge automaton, but you can enumerate through every single term that is within a given distance. So now you intersect this automaton with the terms dictionary, and what you're left with are only these terms that are actually matching. So what you need to do is collect these documents that have these terms, and you're done. So believe it or not, this actually speeds up things. Compared to the naive approach. Okay, Michael is also working on integrating finite state automata into the terms index. So the entire terms index, instead of the posting list sorted alphabetically, could be represented as a finite state machine. There is actually some work done on this that is in trunk, and that accelerates things already. But if you want to track that, it's Lucene 3030. Okay, so summary, and I'm probably done, right? Did you fall asleep there, timekeeper? Good. Okay, so the summary. Finite state machines, it's a fundamental data structure that's been there for years. It's back to, I don't know, 60s, 70s. But it's something that is beautiful in a way. It's a simple thing that you can use for many different tasks and challenges. And it's efficient. It's very well known. The algorithms are very well known. It's probably in every single one-on-one algorithms book that you can find out there. And surprisingly, it's just, doing miracles in Lucene and Solr. And Robert and Mike and Uwe, they all come up with all different kinds of applications. We're actually trying to get compound splitting in German to get it done with finite state machines. So if you're interested in helping, and we need a test data set badly. So if you're interested in helping us, please send me an email and I'll be happy to get you involved. Okay, the API in Lucene is still experimental. I'd like to thank my colleagues for helping me in preparing this presentation. And they're the ones that are actually responsible for the code. And they're great, by the way. So if you have questions concerning the code, ask me. If I'm not able to tell you what's going on, I'll just, redirect it to Mike or Robert. Thank you very much for listening. I hope you liked it. And we should have 3 minutes for questions, right? Yeah, I'm good with time. So if you do have any questions other than level 2 distance, should probably use the microphone.
Thanks for the presentation.
Thank you.
What are other practical usage of these finite state automata algorithms?
Other practical uses? It's like saying, what are the practical uses of lists? We use it for lookups a lot. Like if you have a lot of strings that share common prefixes and common suffixes, that's a great way of actually getting them in memory and conserving it. So instead of a hash set, it's an alternative that is great in terms of memory reduction. If you have a hash set of strings that is huge and consumes a lot of memory, reducing it into an automaton is a great way to keep the memory requirements low. Although that is a pretty static data structure. So the construction time for this 35 million set of, half-gig set of strings, the construction time with Lucene on my machine, which is not really powerful, that's 20 seconds. So that's still not bad. It's flying, but it's not online. So you need to keep that in mind. Okay? Use cases, I don't know. Open up, come up with something. It's really a great structure. Once you know how it works, I'm sure you'll find some use cases for it. Is that the question where I'm going to drop dead?
Be afraid. No, actually, I think that I just wanted to add an answer. Sure. FSAs and DFSAs are used very widely in natural language processing. Right. Almost all of the named entity detectors, things like that. Yeah, I just recalled one. Yeah. The regular expressions. You get really efficient regular expression matching algorithms if you use non-deterministic finite state automata. Actually, that project from Google that is called RE2 is the regular expression matcher that is really prone to people constructing queries that take a long time. People will actually create regular expressions that can effectively stop your server, because in Java, regular expressions are recursive, so it's actually a backtracking algorithm, and it can actually hang your server. So there is a Google code that implements regular expressions as non-deterministic state automata. So it tracks those coins, but with every symbol, it pushes them further. So it's limited only by the length of the input, not by the regular expression or the combinations of terms. That's one great application of FSTs. But there are lots, and Ted is right that natural language processing loves it.
Do these Lucene APIs support incrementally updating or changing these?
Okay, the question was if I can foresee the API support for changing the automaton. Theoretically, it's possible to do that. I mean, there are algorithms for updating finite state machines, but these algorithms usually rely on the presence of the entire data structure in memory in a way that you can, move around pointers. Huh?
The original data.
No, the state machine. But, just as, objects with links and stuff. And what we do is we construct it as a byte array. There is never a representation of a graph in memory. It's just, serialized to a byte array right away. So that's why it's so fast.
And it's not really needed in Lucene because,
it's not really,
for example, for the terms index, all files, as I said before,
are already sorted.
Already sorted and only written once. So whenever you change anything to your index, you
right.
create a new segment.
That's correct. But if you're looking for something like that, the bricks library that I've mentioned, I think it's bricks.dk. And that gives you the full ability to do whatever you want, to manipulate, whatever you want.
Do you think it's interesting to have this kind of automatas on top of a graph DB?
On top of what?
Of a graph database.
Okay, the question was if it's interesting to have these kind of automata on top of a database.
No, of a graph DB.
Graph database? Oh God, it is a graph. He's waving at me. I guess so. I mean, I'm pretty sure that FSTs, transducers, and automata are used extensively in complex data structures to accelerate things. I'm not in the industry. I can't say that for sure, but I don't believe that smart people don't know about it. So, okay, I'll have to stop because he's gonna kill me and he's a lot bigger. So, thank you very much.